So next is highs or maximum strain energy theory. The previous one was maximum strain theory. Now this is, here we have energy, strain energy. Okay. So you have to understand this concept. Okay. So let's draw a graph for steel, like our stress strain curve. Okay. So this is sigma, this is E. Okay, now the strain energy, the energy up to the elastic point. So how we can find out? This is nothing but the area under the curve. Okay, this is let's say this will be our SYT. Okay, so the area under this curve is the strain energy. Okay, now let's find out the strain energy per unit volume. Okay, strain energy per, it is per unit volume. Okay, it is nothing but area under the curve. So it is a triangle. So 1/2 into our base into height. Okay, SYT. Okay, that is nothing but the sigma. Let's consider it is a sigma. Okay, so it is a stress at this point. So we can write it as 1/2 into E. Again we can write it as sigma by E into, again this is sigma. Okay, so strain energy will be 1/2 sigma square by E. So this is the strain energy per unit volume stored in the body up to, okay, at any point. Okay, we are considering this sigma. Now this same strain energy, actually here we have to consider, this is sigma, sorry, we are considering at any point. Now we are considering the maximum strain energy stored up to the yield point. Okay, now how we can write it is, as it is nothing but sigma into this U, it is equal to, this was sigma, so the stress as yield point we have SYT. Okay, so that will be SYT square by 2E. Okay, so this is the strain energy of the body, and this is the maximum strain energy at yield point. This is at yield point. Okay, so what this theory tells, that if the maximum strain energy which is induced in the body is greater than the strain energy at yield point, that means if this let's consider as U1. Okay, so if U1 is greater than U at yield point, then the material is going to fail. Okay, so in order to ensure the safety of the material, the maximum strain energy should lie within, should be lesser than the strain energy at yield point. Okay, so this is very important, and let's have how we can find out the total strain energy. Okay, now this is nothing but the total strain energy per unit volume. So here we have 1/2 into sigma 1. Now we have sigma 1 into E1, because we just like consider a body. Okay, now it is subjected to sigma 1, sigma 2 and sigma 3. Okay, so your total is nothing but the 1/2 into sigma 1 into E1, then again 1/2 into sigma 2 into E2 plus sigma 3 into E3. Okay, this will be the strain energy for unit volume, and this is the total energy. Okay, so in the previous example we saw. Okay, now how we can write it as, this is first is 1/2 into sigma 1. Now E1 we have found out like in previous case, so that will be sigma 1 into E minus mu times sigma 2 into E minus mu times sigma 3 into E. Okay, this is the first term. Then plus we have 1/2, here we have sigma 2, so sigma 2 by E minus mu times sigma 1 by E minus mu times sigma 3 by E plus 1/2 into sigma 3, so it will be sigma 3 by E minus mu times sigma 1 by E minus mu times sigma 2 by E. Okay, so this is the total strain energy per unit volume of the body. So this total energy which we have found out here should be lesser than the strain energy at yield point. Okay, so at this condition only the material will be safer, otherwise it will fail. So if we go into the derivation, we will find out that the representation of this area is an ellipse. Okay, so we will represent it like on the graph. Okay, so it is nothing but an ellipse. So ellipse equation. So this, and again at 45 degree we will have a shear diagonal. Okay, this is sigma 1, this is minus sigma 1, this is sigma 2, this is minus sigma 2. Okay, and we have, this is our shear diagonal. Okay, so like I said, if the stress value falls within this area, then the material will be safe. Okay, now this theory is valid for ductile materials, so it is not much widely used, but it is valued for ductile materials only. Okay, now the next theory is von Mises theory and Henke's theory, or it is also called as distortion energy theory. Now we have seen that we have the total strain energy. Now this total strain energy of the body can be written, or it can be divided into two parts. This is the total. Okay, now this is because of the change in volume of the body plus the distortion of the body. Now distortion is nothing but the shape change of the body. Okay, so this total strain energy is because of the change in volume plus the strain energy because of the change in volume plus the strain energy because of the distortion, that is the shape change of the body. Now this distortion, why this distortion causes, it is because of the shear stresses. Shear stresses tends to change the shape of the body, and because of which there is a distortion. So this part is because of the shear stresses, and change in volume is because of the hydrostatic stresses, that is the normal stresses. The normal stresses tend to change the volume of the body. Okay, and this is our total strain energy. So this theory is related to distortion energy. Okay, so we are focusing on this, so we can write from this equation as UD, that's it, distortion energy is nothing but U total minus U volume. Okay, so here we are focusing on distortion energy, not on the total energy. In the previous theory we are more focused on the total energy. Now here we are considering the distortion energy. Okay, so how we can represent this and what is this theory. Again, the distortion energy of the body, if it is greater than the distortion energy at yield point, then the material is going to fail. Okay, so it should be lesser than or equal to the distortion energy at yield point in order to be safe. Okay, so how we can represent it? It is, we can represent it as okay, and this diagonal, is equal to under root 2 of SYT plus under root, this is SYT. So you can find out this by derivation. We are not going into that depth. Okay, so this is again our sigma 1, this is minus sigma 1, this is sigma 2, and this is minus sigma 2. So this is the representation of von Mises theory, and this theory is valid for ductile materials. Okay, so up till now we have seen different theories which are applicable for different materials. Now there is again one point, that which theory should be used for which material. Like for ductile materials we have maximum shear stress theory, and also we have distortion energy theory. Okay, so it depends on the factor of safety you require or the design complexity which you want. It is totally a choice of designer, that means which kind of application he is designing. So we will just see the difference between the maximum shear stress theory and distortion energy theory. Okay, so we have seen the graphical representations, so let's again have a common representation for these two theories. Okay, so we have maximum shear stress theory. So let's draw the graph. Okay, so this is our sigma 1, this is minus sigma 1, this is our sigma 2, this is minus sigma 2. Okay, so we have a Tresca's hexagon, if you remember, for maximum shear stress theory. So this is our Tresca's hexagon, and we have a ellipse for distortion energy theory, just now we have seen. Okay, so it will be covering, sorry for the drawing. Okay, so it will be covering like this. So this red one is our distortion or von Mises, and this is our Tresca or maximum shear stress theory, and this is distortion energy theory. Okay, so this is the representation. Now we can see the difference on these two on different parameters. Okay, so let's consider different parameters. Okay, parameter, and for maximum shear stress theory and for distortion energy theory. Okay, so first one, if we consider the safety, so this is more safe than this distortion energy theory. That means the design which you are doing by considering the maximum shear stress theory will be safer than the design considering the distortion energy theory. This is the meaning of this. then size, as this is more safe, okay, so its size will obviously will be more, so this will be lesser. Then cost, as the size is more, then obviously the cost is more, okay. And one important point is strength. Here we consider the shear stress as 50% of the yield strength, and here we consider 57.7% of yield strength, okay. So as here we can see, we are considering the 50% of the SYT. This is more safer, we go more safer. Here also you can observe this stress cards hexagon is inside and this ellipse is outside, so we cannot go here, so we always go conservative. So this design is more safe, and it is not necessary all the time we give more factor of safety, because giving more factor of safety doesn't mean that the design is best, because while giving more factor of safety you are ultimately increasing the material, that's why the weight is also increasing, the size is also increasing, and the cost is also increasing. So it is very important to decide the theory of failure which you are going to use, what will be its implications on your design. So it is very important. So while designing, these theories of failure should be considered, and this is very core and very important topic for any design. So if you have these concepts clear in your mind, then designing is more easier, okay. So I hope I tried to cover all the theories. I haven't gone into the derivations, that how this shape has come up, but because if I had included it, the video might gone longer and lengthier. So I tried to cover more basics, that how this shape and what is the meaning of this theory, then how it can be derived, what is the basics, how the strain energy is calculated. So I have more emphasized on these concepts. So I hope you understood these concepts, and I again request that in order to understand this topic, do watch the previous lectures of principal stress and Mohr circle, so that it will be easier to understand these concepts. So if you have any doubts, please do write into the comment section. Until then, be safe and stay happy. Thank you.